All right, hello everyone. My name is Kate Kreider. I'm a student in Scott Didham's group at CU Boulder. And today I'm going to be talking about modeling chromatic mode frequency shifts in etalons for high precision spectrograph calibration. Before I get started, I'd like to give a very broad and kind of maybe overview of the general landscape of calibration sources. I'll start with the most conventional, that being lamps and gas cells. Lamps and gas cells have the advantage of being very low cost, quite simple. However, they do have some intrinsic precision limitations, which is why I've shown them on the bottom left of this sort of cartoon plot I have here of spectral information versus stability. They do, however, have good stability over time. On the other end of the spectrum, we have laser frequency combs, which are robust, have a high precision level due to the fact of their fine mode spacing and the ability to accurately reference them to the SI second. And kind of to illustrate the difference between these two, I have this image from the Redmond paper here on the bottom right, which shows the spectrum of a laser frequency comb on the top against I believe, uranium neon lamp on the bottom. And what we see is that the laser frequency comb has sort of a relatively stable amplitude and spacing where the lamp does not. However, laser frequency combs are expensive and complex, which sort of motivates a middle ground between these two sources. And that is where Fabry-Pro etalons come in. We know that they're simple and much less expensive than laser frequency combs, but are capable of achieving a similar precision level. However, they do not have any intrinsic accuracy, meaning that their stability over time is a little bit more of a problem. I'm also going to give a very broad overview of Fabry-Pro etalons in general. So we know that they're an optical cavity formed by two parallel mirrors, meaning that their mode spectrum is given by, or is this series of finely spaced modes given by the resonance condition, which I've included on the top right of the screen. In that resonance condition, we see this L that comes from the cavity spacer length, M, which is an integer, and phi sub R, which is the mirror phase on reflection. And this is a quite simple condition for the mode locations. However, as we know, it's tied to the physical properties of the etalon itself, which is why the stability over time is a question. I'm not going to go into specific details of the etalons I'm looking at in this presentation. Those will be the HPF and NUID spectrograph etalons, but if you're interested, I would encourage you to check out this Jeff Jennings paper from 2020. I'm similarly not going to go into a ton of detail on the actual architecture of the HPF and NUID spectrographs. I sort of wanted to gesture at how the etalon is incorporated into these structures. And so that's what this is meant to indicate. It's illuminated via single mode fiber and then coupled into multi-mode fiber before being sent to the detector array. But like I said, outside of the scope of this talk. So I mentioned that the stability of an etalon over time is a question because the mode locations are tied to the actual mechanical properties of the etalon, which are things that can change. And if you ask yourself what might be the most likely cause or most likely source of drift in a Fabry-Pro etalon, you might think of the spacer length L. And what that manifests as a fractional change in the frequency is a kind of a constant value. So I've indicated this in the two images I've shown on the bottom left, or on the bottom of the screen. The bottom left shows a cartoon image of this drift over time. So if our red mode is shifting by some defined amount delta, then the next mode is shifting by twice that, the next by 3 times. And what that looks like in the fractional frequency or Doppler picture is just a flat line, which is good news for calibration because the behavior of each mode is tied very predictably to the behavior of the others. However, measurements made at several etalon systems indicate that this simple picture of mode drift is not actually the case. This slide is kind of, it relies on the measurements made on the HPF etalon specifically. And so I've included a similar cartoon on the left that shows that, if the red mode is drifting by that same amount, delta N, the next might be drifting in the opposite direction, the next might not be moving at all. And what those actual measurements look like is kind of indicated in this plot on the right that shows the mode frequency or the mode shift in fractional frequency units across the wavelength spectrum. This poses a challenge for calibration because there's no straightforward connection between the drift of each mode. And like I said, the previous slide focused on the HPF spectrograph, but we've seen it in multiple etalon systems. So on this slide, I've included HPF, NUID, and espresso. Here there are more, but I'll specifically be focusing on the HPF and NUID etalons for the rest of this talk. And yes, my specific project was to look at modeling possible sources of the drift that we're seeing in those two etalon systems. I did that by looking at a complication to the resonance condition. So I flashed this equation on a few slides back, but I didn't include the fact that the phi sub r, that mirror phase reflection term, is wavelength dependent and varies quite a lot across the wavelength spectrum of the etalon. These two images are specific to the HPF, but you can see if you look at the red line on the plot on the bottom right, that there's quite a wide range of variation in that phase across the wavelength spectrum. So this sort of poses a natural suspect for the wavelength dependence of the mode drift, and that was what I was looking at modeling changes to. So my general method was to use the optical transfer matrix method to model perturbations on the mirror phase due to perturbations to the physical structure of the mirrors, and then look at the subsequent effect on the mode locations. I've included a schematic on the left here that sort of shows what a mirror coating might look like. This one kind of makes it look a bit simpler than it is. Between HPF and NUID, we have two structures that are between 30 and 50 layers each. And although this plot doesn't show it, they vary a lot in thickness, anywhere from less than 10 nanometers to over 500 nanometers on a single layer. So I highlight all of that to say that it's a complicated modeling problem. And because of that, we wanted to orient our modeling to the position of physically reasonable explanations, because you can imagine there are enough knobs to turn that it would be possible to explain this behavior in ways that might not have a physical meaning. I'm going to tell this story in a little bit of a reverse order. So I will be showing the solutions that we found here in the next slide, but I want to kind of touch on the things that we tested. Otherwise, I'll revisit this later. So we looked at variations across the structure, including things like temperature gradients, manufacturing tolerances, using numbers given to us by the manufacturer, and variations in incident light like polarization and incident angle. So I'll start with a physical picture of what we think might be going on in the HPF and NUID etalons. So our models suggest that there's a gradual expansion in the outer layers of the mirror coating, which are compressive, and that expansion causes a subsequent refractive index decrease due to the decreasing density. This would be the mirror coating layer that's closest to vacuum, so the vacuum would not be offering a resistance to this compression, and gradually over time, we would see it expand. And this was, something that we stumbled into in the modeling, but in doing so, and talking to people like Chris Schwab and Daniel Mitchell from Light Machinery, it became apparent that this sort of mechanism, or a mechanism in the outermost layers of the system, might be something that other people had, was well known to the community, I guess, in advance. But here are the specific modeling results for the HPF etalon. So I've included on this top right plot the data from Ryan Tarian's paper on the HPF drift, and then two fits that I have produced for allowing for changes in just the outermost layer of the mirror coating and then the outer two layers of the mirror coating. What we see is we're able to reproduce this drift quite well. And specifically, the parameters that we fit for these results are given on the table on the bottom left. So this gives about a bulk shift of about 2.9 centimeters per second per day. And then thickness changes in each layer on the order of 10 to the -4 nanometers per day, and refractive index changes on the order of 10 to the -6. And I'll say one thing about these relative magnitudes of these two numbers. They do sort of agree with the model of if you use that delta D as a parameter for what refractive index change you might expect, it comes out very similar to the refractive index our model produces independently. I'll also note that you might be able to see, particularly in the one-layer model case, a bit of a phase offset between the data and the fit. We did find that manufacturing tolerances, specifically a 1 nanometer uncertainty on each layer deposition, manifest as a phase offset in the mode shift. So that could be one possible reason for a discrepancy. Here are similar results for the NUID drift. Again, I'll point to the numbers on the bottom left of the screen. It's very similar scale, so about 1.7 times 10 to the -3, change in the thickness, and then a subsequent refractive index decrease. And yes, again, very similar results to the HPF as well. I'll note then, I mentioned that I was going to talk about a few other things that we tested that might be happening. None of these appear to be the dominant effect in either of the etalon systems. However, they might be hiding in the residuals. So one of the things that we looked at was the temperature gradients in the mirror coating. So I'm going to show the case of just a uniform temperature change across the cavity. For simplicity's sake, we tested a few different ways temperature could be changing. So this plot on the bottom left is the result of a uniform 1 millikelvin change across the cavity. We do see that it has some chromatic dependence, particularly in the lower wavelength region, but not too much qualitative similarity to the the HPF and NUID drifts. And I should mention these 3 plots here were specific to the HPF etalon. We also looked at incident angle variation. So again, we see that there is some chromatic structure across the spectrum. However, if you look at the vertical axis, you see that the primary effect is a vertical shift. So a bulk shift due to the effective length or change of the cavity spacer length. And then we also looked at polarization variation. This one shows perhaps the most interesting chromatic structure. This is the difference between completely S-polarized and completely P-polarized light at 1 milliradian offset. And we see that that does produce something, sorry, these are in fractional frequency units, but if you translated it back to Doppler shift, it's on the same scale of the changes that we observe in the HPF and NUID etalons. However, you do need a minimum of 1 milliradian misalignment for that difference to reach the magnitude of the measured drift, meaning that this is maybe not a key factor in the measured behavior. So with that, yeah, I'd like to wrap things up. Our models do suggest that for the HPF and NUID etalons, that the source of the chromatic drift is the gradual relaxation of the outer layer of the mirror stack. We looked at several other potential physical causes, including incident angle, polarization, temperature, but none of them explain the dominant effect there. And yeah, in general, this offers insight into potential parameters for mirror design. I'm happy to go into that a little bit more. Possibility of and opens the possibility, if we were to get better models for these systems, of incorporating chromatic drift in calibration. So with that, I'll close things off. I'd like to thank all of these organizations I've included on the slide here, as well as Scott Diddams and his group in Boulder. And I'm happy to take any questions. Thank you.
And perfect timing. Thank you very much. Okay, questions? Francesca.
Thank you. Brilliant. Very good. Very interesting. And we had already consequences for our espresso spectrograph of all this. Question. It's actually a 2-part question. You assumed just the change of the 2 layers, the outer layers. Would it give the same result if you had a, let's say, a homogeneous expansion of all the layers? Would you have some kind of degeneracy? And the other is, did you consider the possibility that there is, because these soft coatings, they seem to outgas, would these produce the same effect, outgassing?
Yeah, I guess to your first question, I don't think a homogeneous change across the structure produces the same results. It's sort of, the fitting can get a little bit finicky because I don't know, it tries to overfit the data essentially if you include more layers, but we looked at kind of the effect of changing each layer individually, and definitely the behavior that we see in the measurements on both etalons are specific to the first few layers of this system. So certainly something in the first few layers, not something you would want to include the whole mirror stack for. Outgassing, I think, I don't know, potentially not. I think we looked at that a little bit as a possible explanation for this behavior in the outer couple of layers, but yeah, not sure about that one.
Okay, do we have any questions online? No. Okay, we have one more over here, and then we'll have to move on.
This is really cool work that you put in a lot of effort to look at really fine details of things. You figured out what was the problem and what might be a solution. Do you actually want to change anything now that you know and have quantified this really well? Does your team actually want to take a solution towards changing something?
Yeah, I guess I'm not 100% sure the next future steps. I don't know that this, as it is now, is enough of a solution to kind of include this in the calibration step to, correct out this problem. So I assume there are future steps that are needed one way or the other there. One thing I'll say is that the complexity of the phase terms in both of these mirror coatings does seem to, I don't know, it sort of gives the structure that the drifts have. So maybe in future etalon systems, kind of trying to reduce that complexity if possible, would allow for more stable etalons, which I think would be a benefit. Yeah.
Okay, I said that was our last one, but is it quick, Andreas? Okay, make it quick.
Well, first, excellent work and great talk. Really appreciated that. I think one of the differences, because Francesco asked about the soft coatings, is those are hard coatings, right? And for those etalons, so they don't have the same problem. So when we later also hear the talk by Tobias, we have to keep that in mind, that those are very different types of etalons, right? Between NUIT and HBF on the one hand, and the soft coating etalons we typically use in the other spectrographs.
Thank you.